All right, good afternoon, everybody. It is my great pleasure to introduce my fellow colleague from IMPAN, Jarosław Buczyński. He was born on 8th of January 1980, so he is the age of my brother. He was born as a mathematician in 2008. He got his PhD from the University of Warsaw. Then he obtained his habilitation at IMPAN in 2015. Sorry, I don't remember how I voted, but I guess it was yes. And he will become a full professor in June 2026. He is head of a Department of Algebraic Geometry Research Group at IMPAN. He is a recipient of really numerous research grants, Polish and European, and which is, in my opinion, very remarkable. He brought up 5 PhD students, so taking into account his young age, that's really remarkable. So it means he must be a very good supervisor. So if you are looking for a good supervisor in algebraic geometry, that's a good suggestion. And among his 5 PhD students, there was Joachim Yelisiejew, who was our speaker a year ago. So we somehow continue this algebraic geometry theme. And Jarek, it's all yours. Take it away.
Thank you very much. Thank you for inviting me here and for the very nice introduction. What I want to talk about is more or less general problem. No, I have to move. Work now? Okay. Very roughly, the problem is as follows. So we have a finite dimensional vector space. And well, I will, as a mathematician, prefer the vector space to be over complex numbers. But in the application, we often want real numbers, so there is a little bit of interchange. For simplicity, at the later stage of the talk, I will only restrict to complex numbers. And I'm picking some subset of V. I will want more properties of this X at later stage, but for now it's just a subset.
Bo my slajdów tu nie widzimy na Zoomie.
Stop share post. How do you unstop it? You know?
Can you see it now?
Can you see it now, or?
Yes, now it's okay.
Sorry about that. Okay, let me continue. So I have a vector space, I have a subset of this vector space, and I want to think about V as a space of all possible observations, states, whatever. And then X is some subset of stuff that's quite simple. So now if I'm given an F, I want to write it as a sum or linear combination of those simple elements Pi, with each Pi in X. So it's kind of the, as a baby example, we can think of a soup. It's relatively easy to make a soup out of vegetables. And now I want to do the opposite. So I'm given a soup and I want to extract the vegetables out of this soup, which is much more difficult. And then more serious examples that appear in real life. If you have well, many of you have mobile phones in your pockets right now, and then there is like a single antenna that collects all the signals from your phones, and if many of you at the same time start talking through your mobile phone, then the antenna must decompose these superposed signals from many cell phones into separate conversations. And another example where this appears is in chemistry. If you are given samples of some substances, typically it will be water with something, like water with some minerals, water with some pollution, or water with some other stuff. and there are many samples, and each of them contains different proportion of some unknown chemicals. Then you want to determine what are the concentrations of each chemical in these samples. And one method to do it, and one application of fluorescence spectroscopy, is to use this spectroscometer, whose schematic is drawn on the left hand of the picture. And the idea is that you have this light source here, and then the light source is filtered by some preliminary filter, so that you only get one wavelength of the light coming out of after this filter. Then the sample the sample has some fluorescence properties, and out of it again there comes light with various wavelengths, and then you want to extract just one of them. Okay, whatever. And then you measure how much light came out of this process. So what you get eventually is an array with numbers, and the array has 3 dimensions. One is the parameter of the sample. You have many samples to try, and then the other one is the parameter for the excitation filter. So you can filter out one wavelength, another wavelength, or so on. And the third parameter comes from emission filter, which can also vary. So we have eventually, in mathematical terms, you get an order 3 tensor, for which you want to decompose and eventually read out the data, the fluorescent properties of each chemical that's involved in this mess. Okay, and then in more mathematical application, we have the matrix multiplication, which is some simple operation. This is written out explicitly for 2x2 matrices, and you have certainly seen this at some point. It's one of the first things we learn, but maybe we don't learn it in a computer optimal way. So the way we learn it is this formula, and as a tensor, this matrix multiplication is this order 3 tensor, which is written out explicitly, and we are using here altogether 8 simple tensors, 1, 2, 3, 4, and so on. And then using this method, if we get large matrices, say 1000 by 1000, then we approximately need a billion of multiplications to execute, and the computer scientist would like to get it much lower than that. So Strassen was trying to prove that that's impossible for 2x2 matrices. Instead, he proved this formula, which only involves 7 multiplications. So you first, on your paper, on your side, or in the computer memory, you calculate these 7 numbers. Each one of them requires a bunch of additions, which are not expensive, and then a bunch of multiplication, or just one multiplication for each number. So altogether there will be 7 multiplication, and it turns out that product of 2x2 matrices is exactly this. And using, well, of course, 2x2 matrices are not a problem for computer, but using the same method, you can use it blockwise, and then if you split large matrices into 2, and then do it recursively, you get something like 300 million multiplications. So it's more than 3 times less than.
Sorry, may I have a question?
Yes.
Two questions, in fact. So how old is this algorithm? Is the first one, and then what is the precise form of this exponent? Since you have written approximately.
Yes. Okay. So Okay, so it's a little subtle. So, okay, first question is easy. So it's, I think, 1969, if I remember correctly. It's published in the paper from 1969. And the second question is, this is roughly a logarithm of 7 with base 2, which 7 is the number of those guys. So you just simply divide it and you do it. But there is a little caveat because now the additions are becoming more relevant. So there is a little epsilon to that, which is responsible for the additions. And the additions become less and less relevant if you increase n.
Okay, thank you.
So, so this is the summary of this matrix multiplication algorithm. And then written as tensor, this is this presentation of this tensor, order 3 tensor of matrix multiplication using only 7 simple terms, right? And with this formula, we can, okay, so well, this is the brief explanation how this tensor is created. For if A was if A appeared here, then we put C1 times A in the tensor and so on, right? Also A appears here, so we add C4 times the same thing, and for B is very similar, and so on. And then you can verify that this is actually the same tensor. You just do your well, calculations, elementary calculations. You can see, for example, that this term appears here, here, and here. And this is the only place where A3 times B1 times C3 appears at all. So this is at least coefficient with this term is correct. And you do it for all the other guys. This, for instance, this one, A1, B1, C4 appears on the bottom expression, but it doesn't appear anywhere on the top. And on the bottom expression, it appears once with plus sign and the other time with minus sign. So you can just do it for all the terms or just plug it into computer and check that this is correct. Okay, so formalizing a little bit, this is just the same thing as first slide. And so we have a vector space, a subset of this vector space. And the problem that we consider is this decomposition problem. We have some complicated object F, and we want to write it as a linear combination of simple guys from X. So in the example of the antenna, there's PIs. The F will be the signal received by antenna, and then P1, P2, P3, and so on will be the individual phone calls, and maybe the lambda i's will measure how strong the signals, each signal is. In the example of the fluorescence spectroscopy, we have the F will be the data, the tensor that we obtained from just running the experiment, and then lambda I times pi will be the spectral data of each chemical in the sample. So it's a little bit more complicated here, but I can explain it afterwards in more details. And in the algorithm, we have a complicated multilinear algorithm, and then the PIs will represent the multiplication, at least. Each PI will represent a single multiplication that's needed for this particular algorithm. So you can see that this is all part of the same problem. And what are the mathematical questions to ask? Well, first of all, we would like to know the R, so the optimal one. Of course, our set typically is infinite. It's kind of it will be submanifold of the vector space or something like that. Some large topological space, which usually will span the whole vector space. Otherwise, this expression would not be possible at all. So we want to find an optimal R such that this is as small as possible, and it's it will be, this number will correspond to the number of phone calls, number of chemical substances involved in the solutions, or number of elementary operations required to execute some specific algorithm. So this is one of the possible questions to ask. Another one would be to find the decomposition. Once I'm given an F and given an R, what is the what are those ingredients P1 up to P2, P2, PR, and also the scalars. These are usually easier to determine. And then we can ask more questions. Is this decomposition unique? Well, okay, so there are some trivial things you can do. You can swap the factors in order. You can, maybe there are more symmetries of the problem. Maybe you can encompose your scalar into this PIs in some way. So there are some obvious things that you can do to change the decomposition seemingly. But other than the obvious stuff, can we find many solutions to the problem? That for applications that would be usually bad. This means that we have too few, that we have collected too few data for the problem. And then there is also noise. The question of is how accurate is our data that we collected? How accurate is the composition that we want? How accurate the composition we want, and so on. So from these problems, I will focus on the first two, and in fact mostly on the first one. But these are all very important problems, and these are not the only problems that we can produce out of this simple phrasing of problem. And there is a lot of things to do in this area. So let me focus on these first two for a while. And I will give you one and only one example how to do it from the beginning to the end, with only skipping a little bit of details under the rug. This is actually, well, I don't want to say it's the only example we understand at all, but it's almost the only large family of examples that we understand from the very beginning to the very end. We can do everything here. I will present for you most of the fact that we know, but then there are some long but not very difficult path that we can follow from that. So the example is a vector space of polynomials of degree at most d, and we want to present elements of this vector space as sums of powers. So the degree d, so we have to use diff powers of linear forms, the same d, and then with this, well, okay, so this is well, the simplest version of the problem. Of course, we could try to do it for higher number of variables like x, y, z, and so on. And I will just do it here for one very single variate polynomials. That's not quite true, but well, you will see. So let me give you two examples that will be kind of illustrative for the method. So first, let's take a cubic, x cubed minus 18x squared minus 36. And then, well, okay, so I have to be honest, I created first the decomposition, then produced the f, but that's because I wanted the numbers to come out nice, not like huge numbers, but this is not so important. So, okay, so let's just take it as a black box for now, but let's keep in mind that we really want to, well, someone gives us, this number, this polynomial, and we want to get this expression, right? So this is the, here I'm giving you it on the plate, just to show you what's going on. And but in general, well, we don't know the expression as sum of powers in the first place. So the first trick or minor trick that I want to do with this is work with homogeneous polynomials instead. So I'm adding an extra variable y, and I'm making all these polynomials homogeneous. So instead of x square y, instead of x square, I write x square y if d was equal to 3, and so on. So we get these expressions, and of course this is the same form. These are eventually the same formulas. So in the homogeneous setting, the general problem would be that we have this old problem that was before, but I'm adding y's in all those locations where the thing was non-homogeneous. So I get homogeneous expression. So why is it better? Well, so before I could take derivatives with respect to x, and that was some information, but now I can take derivatives with respect to both x and y. So, so of course, I mean, I could avoid introducing x and introduce some pretty non-natural operation, which would do the same thing as deriving with respect to x, but instead it's easier to explain it this way. So I have these two operations. I denote them by alpha and beta for brevity. And then going back to our examples, I want to carefully find a derivation, a combination of this alpha and beta, which makes turns my f into something simpler, right? And now I should define what is simpler, but instead of defining it, I will just show you on this example. So I had this expression using two terms. So r was equal to 2. And now after using this particular derivation, I obtain eventually something that has only one term, and surprise, this is essentially the same term as here. The constant has changed, but constant is the easy part. And then I want to this is the effect I want to achieve in general. So now let's go to the more serious example of degree 7. And now I know what to choose, so I've chosen the right one. And then if I apply this, but now I'm cheating because I know the expression that I want to get. So I'm working with this expression final. So I get this this operator applied to each of the 7th powers. And if you focus on this term, you will see that this is actually 0 because by Leibniz rule. So there will be a factor which is d by dx minus d by dy of x plus y times something else, and then this first derivative is 0. So this vanishes, and this is how I'm choosing my my derivations alpha minus beta, right? So I chose it in such a way that it will kill me one of the terms. And then at the end, I get only sum of two guys. So what I'm looking at, I'm looking for differential operators, which makes my polynomial much simpler and easier to deal with. Okay, so this is general fact. Now, okay, there were examples. Now it's just a little bit of theory with this notation that alpha is the d by dx and beta is d by dy. I have, first of all, if I have a diff powers of this form, if I swap the coefficients and the sign, so I take the perpendicular form, then I obviously get 0, but this is not only one direction, but it also works in the other direction. So if I have any derivative, then this will be 0 if and only if my coefficients after swapping them and taking minus to one of them are proportional to b and c. And the theorem, which in much more general setting is called apolarity lemma, is the following. So if I have any f, any polynomial of the homogeneous polynomial in two variables of degree d, and I pick some non-proportional Li's, so I don't want these guys to repeat one another, then we have a decomposition of this form if and only if this differential operator, which is here, this is the main reason why I introduced alpha and beta, because otherwise it would be impossible to fit it on a slide with the I deleted it. Then if and only if this this operator kills my f, so annihilates my f. And this is what, well, the proof is essentially as is just applying. Well, okay, one direction is easy from what's written above, but this is also the other direction is.
Sorry, could you explain what exactly I mean by non-proportional?
Right. So if I take L1 equal to twice x plus y and L2 equal to 4x plus 2y, then they are proportional.
So Li's for different i's, they are mutually non-proportional. Okay.
Right, mutually non-proportional. Sorry for that. Okay, so this is the method of finding the rank and decomposition. Well, okay, this is like simplified version of the algorithm. This is not exactly what you would implement, but well, sufficiently close to what you would implement. So you start from f, and maybe you have some guess for your r. So you start from some r, maybe r equal 1 if you want, maybe r equal 2 or something. And you're looking for a form theta, so which is a combination of degree r with some coefficients of alpha to the r and so on, alpha to the r minus 1 beta and so on. And you're looking for such that annihilate your f. So this is a differential operator, and you want to I don't know how does it work. Okay, you want to find one that's 0 when you apply it to f. And if you don't find such, then a polarity lemma tells you that there is no decomposition to sum of r powers, so you should try larger or greater r. And if you find such r, then you want to, well, so we can always express theta as a product of linear forms, if at least over complex numbers. Here is where complex numbers are easier and real numbers are more difficult. But you try to express it as these guys, but also in the polarity lemma, there was this condition on non-proportional CIs. So I will come back to this a little bit later, but let's just not worry about this non-proportional. For most of your Fs, you will have this non-proportionality assured. I mean, there's a measure 0 where the set where this is going to fail. And then you take Li's, and then which are the perpendicular to this CI/BI, and then it remains to find the coefficients. Okay, so there are 3 calculations here, and one is no, it doesn't work still. That one works for some reason. So, okay, so there are 3 steps here. Step 1 is to find such theta, and this is a linear algebra problem because once you have AI's fixed and you are looking for mu r up to mu 0, then this is just well, this is a set of linear equations that you have to solve and to find out if such theta exists. Now, this is a nonlinear problem.
I believe the upper must be not on the hand, but on the dart. And then instead of shaking the screen, you can write on it, yes.
This switches.
Because maybe you push a button on this.
Okay, I see. So I shouldn't touch the button.
Yeah, exactly. And
Thank
put it on the dart, please. Yeah, now it should work.
Okay, whatever. So this part is not reader, right? So you decomposing a polynomial into, well, finding roots of polynomials is, well, there are methods for that. There are approximate methods for that. There are algebraic methods for that. And it's possible to do, but this is probably the most expensive part. And this part is also linear. So the main difficulty is the decomposition. And also the number of times you have to implement this in order to find the correct R. Okay. Now, this was algebra. And as you may know, I'm an algebraic geometer, which means that I try to combine algebra and geometry. And my experience is, maybe that's not everybody's experience, that algebra is very powerful, but provides a little intuitions what to do. So instead, I'm trying to get the intuitions from geometry. And for this, I would like to introduce the second concept, which appeared in my title. The first one was decompositions, and the other was secant varieties. And then let's focus what a secant is. So Euclid called it a straight line falling from a point on the circle and cutting it. This was more or less the way that Euclid called it in his books. And then in the modern language, in this would be a secant of a curve on a plane. And I would like to stress that it's also a secant line on the curve in this case. So yes, so in Polish, this is called sieczna. I know it might be confusing for some people who have never seen the English name. But this is plane circle, which is not so much a research topic. And there are, of course, many secant lines to a circle, and in the limit you get something that's now called tangent line, and it also appears in Euclid's work, a straight line falling on the circle and touching it. Okay, so this is the tangent line is roughly the limit of secant lines, and that's fine. So in more general situation where X is a subset of vector space in higher dimensions. So I'm drawing here a 3-dimensional picture, which is too small to express everything that I want, but let's just imagine this is in much higher dimensional space. So I have a secant line. It's a line that's, okay, I also have the tangent lines here in the same way as for the circle. And I want the secant line to be the affine span of P1 and P2, where these 2 points are points on X. So I'm picking 2 points on X. I take the line from these 2 points, and then therefore I get the secant line. But also I can do it with more points and take the affine span of many more points. So the secant plane would be just an affine span of 3 points. I would probably want them to be affinely independent in order to not span just a line. And what I get as a secant variety, the secant variety Well, in this case, I should better make sure that V is sufficiently large vector space and X is a sufficiently small subset. It will be like much smaller dimension than V. Otherwise, the secant variety will be a trivial thing. So the secant variety of X, the second secant variety of X, is the closure of union of all the secant lines. So I'm drawing all the lines that join 2 points on the variety X, and then I'm taking the union, and on top of that, I'm adding everything that's in the limit. And the same way, I can do the third secant variety, where I can take 3 points and take the affine span, and then add in the closure. So well, in the previous case, in the closure, I could only get tangent lines, essentially, up to some assumptions on X. And here, already in the third secant variety, the number of types of points that can appear in the limit is much, much richer, and the limits get more difficult. And then, of course, if we did it for 2 and 3, we can do it for any R. The R secant variety is just the closure of the union of all the secant R-1 planes in this case. And this is just the planes that are there, the affine spans of R. The reason why I wanted small and large, small X and large vector space is that well, if I take, for example, a curve in a 3-dimensional space, then typically, unless this curve is very, very special, this secant, already the second secant variety will just be everything. So it will be very interesting. So that's why I want the large and small sets.
Could you please explain what you mean by affine span versus linear span?
Right. So before I explain that, let me show you the next slide, which I was about to say I'm not really want to speak about affine span. I prefer linear spans, and in the examples that I'm interested in, this will turn out to be exactly the same thing. But affine span of points is the smallest affine subspace that passes through these points. That's.
I have a question. Can this be treated as like somewhat a generalization of a Grassmannian? Like instead of taking a subspace, you take some variety and then take subspaces in some way?
So the answer is yes and no. So there are some objects on the Grassmannians that we can generalize and make it into something like this, but this is not just so simple. So in Grassmannian, for Grassmannian, typically you want a subspace of a vector space, right? And here I'm getting out of X. So it's a little bit more frustrating. And also I'm taking Q union, and I didn't say that this space is not the same as space spanned by some other points, or maybe they overlap and then there is a curve. So it's slightly more refined. But there is a relation with Grassmannians, but I don't want to go into it. Okay, so we'll just repeat that I prefer to think about linear spans than affine spans, and from now on, this will be the definition of linear spans. For me, I'm a projective algebraic geometer, which means that I'm really interested in sets X, which are invariant under rescalings, and then this union and the previous union is exactly the same thing.
So probably confusion could arise from the fact that Grassmannian consists of points which are identified with subspace, and here I think this is not the case. Yes.
No. Here I'm kind of taking union of some lines, right, or some spaces. So it's not So it's what you would have to do. You would need to take a universal bundle over the Grassmannian, map it into the projective space. Then you have to pick some sub bundle pull back this universal bundle to some smaller set. So it's a little over the plan, over my plan over this talk. I can explain this in more detail, but not here.
Sure, thank you.
Okay, so let's go back to our original problem, the one that's been on the slides already 3 or 4 times. We have vector space, a subset. I would like to assume that this subset is spanning my W. And I'm looking at the secant varieties of X. So as we have seen geometrically, this is some geometric object that corresponds to a set of all the states, all the elements of the vector space that can be decomposed using at most R simple elements. And then I'm adding their limits. So the states was maybe a little bit, this is of course a recycling of some old slides, partially at least. So there was a version for with more applications in mind, and there was a mention of quantum entanglement at some point, which the states coming from this mention. Sorry, this should be. I should have changed this states to some other words. Vectors would be mathematical word, but maybe like this. This is so V is a set of soups, and then the X is a set of vegetables. Okay, so that's something like that. Okay, and then okay, so the secant variety is those decomposable states and their limits, about which we don't want to worry too much, but you have seen in this example that I've calculated that there was this special case with where there was non-proportional. Well, okay, so the general case was non-proportional. We had non-proportional component square free theta, but then the limits correspond to those that are not square free. So if there is a repeated factor with this decomposition that was for some polynomial, then this is exactly what's happening with the in the limit. Okay, and then of course we have that if we have some decomposition, then this F is in the secant variety. The other direction is not true, not necessarily true. We can also have the limits. And what we want to do with these secant varieties, so one thing that we would like to know, and in some cases this is probably the easiest question if you are given a specific X. It's worse if you are if you want to work with some families of different X's with some common properties. So we want to know for which number, what is the smallest number, or maybe at least some number that the G secant variety fills in the whole space. That's why I want the span. Let me try again with this pen. This is why I want the linear span of X to be whole V, so that the G, a finite number G like this exists. So such G is called generic rank, generic X rank. And another thing that we want to find is some kind of criteria if to determine if a given F is in secant variety or not. Right. So this is roughly the short version of this would be to find equations describing secant varieties. So there's some formulas that tell you if you have a point that's in V, can you put it in does it live in secant variety or not, in the fixed secant variety or not? Another thing, more geometric, would be to describe local structure of this secant variety. Well, if you are a singularity theory, it could be types of singularities. And for this to work, as far as now, we have very little hope to achieve this in general, but you need much more assumptions about the not only local structure of X, so like smooth manifold would be some information, but also how the global structure of X, how is it embedded into our V is very important issue here. And then these three problems, from these three problems from now on, I will only talk about the middle one. I will talk about finding equations. And I will present one way of finding these equations. This way starts from a matrix. And the matrix is such that its entries are linear forms on V. So it's not a matrix of numbers, but a matrix of linear forms. So if I get any F in V, and I evaluate each entry of the matrix in at F, what I get a matrix with coefficients whose coefficients are numbers, and moreover, since I assume that the forms are linear, each individual form is linear. This behaves in a linear way. So the matrix evaluated at the sum of two elements will be the sum of two matrices, and so on. And there's an easy observation that if you have two matrices, one of rank K and the other of rank L, and you take their sum, then the sum will be of rank at most K plus L. So this is an easy exercise you can give to your so if you are running linear algebra classes for first year, this is something that they should know after the linear algebra classes with you. This is an important observation. And this leads to the fact that if I have F in secant variety, then the rank of, so the assumption is that my X lives in the space, in the subset with bounded rank of M. So for any point in X, I have rank of M evaluated at this point at most some fixed integer K, okay? Then if I have this property, then for all F's in the secant variety, we have the rank of M of F at most K times R. So it's if you think about this for 3 minutes, then this becomes obvious because we have so it's obvious for, okay, I can't do that, sorry. It's obvious for the elements in the which are not the limits. So for the honest points on the honest secants, by this rule that I mentioned just a second ago, and then in the limits it follows because of the continuity of the rank, so semi-continuity of the rank. So the rank is given, the set of points with bounded rank is given by equations which are minors, and the minors behave continuously. So if the minors vanish, they also vanish on the limit. So that's why we have it on the whole secant varieties. Okay, so how to find, so we want to think about this method as some criterion. So if I'm, in particular, if I'm given F and I know such a matrix M that satisfies this property, I can ask what is the rank of my matrix evaluated at F. That's one method of determining if F is in my secant variety or not. So it's more like or not than if it is, because it's only one way. It doesn't work the other way so far. But maybe we can hope that if we take sufficiently many M's, with symmetrically many different m's, we can get also the other implication. And so first of all, how to produce some interesting m's. Okay, and this is some of them are easy to write explicitly, but if you want a general construction, you need to use something more serious. And this is coming from algebraic geometry, and that's if you know something about algebraic geometry, this comes from multiplying and evaluating sections of vector bundles, maybe also of some coherent sheaves in some cases. And then the other method is, okay, so for each of these methods to work, I need to assume something about x. So in the first case, I need to assume that x is an algebraic, maybe even projective, cone over projective variety. So there has to be some additional information about x. And in the second case, I need a group, a Lie group that acts on my x. And so in other words, I need x to have many symmetries, like infinitely many symmetries. And then the second method is coming from representation theory of Lie groups. You can take you can take tensor product of two representation, which splits into sum of irreducible components, and then if you choose the right tensor product and the right component, then you can produce some matrix which helps you to find equations for secant varieties.
Excuse me, you mean the smoothly groups, not any algebraic groups, yes?
So it depends what's your setting. So throughout my talk, I've never assumed anything about X. And if you want to work with some smooth submanifold of V, you would want to use smooth Lie groups. If you want to work with algebraic or holomorphic submanifold of V, which would also be a cone over some projective algebraic variety, then it's a good setting to talk about algebraic groups, and it's more convenient. I mean, you can also talk about smooth Lie groups, but you have more structure if you use algebraic groups. And
Thank you.
okay, but the problem with this method is that it's not gonna work. It's never gonna work. I mean, it works in the sense that it will give you some bound, some upper bound, or some lower bounds on your R. But there is an abstraction which we called cactus variety, and then it's defined in a very similar way to secant variety. We have this theorem for secant varieties, but there is this typically larger set, and then which is called Arf cactus variety of X, such that if we take a point in X and the matrix is such that rank of M of P is at most K for all these points, then the upper bound on the rank of M will also be satisfied for all points of the cactus variety. So it's kind of an this difference between cactus variety and secant variety is a geometric abstraction for nicely describing the secant variety. So if you look at the picture of the cactus, this is the green part is the secant variety that we want to get through, but there is an abstraction that prevents us eating this nice juicy green part, and these are the spines of the cactus. All right, so I would like to thank you for your attention so far, and this will remind me, Piotr, what's the name of the conference?
Baby steps beyond the horizon.
I see. So this is the horizon, right? So this is the picture more or less of the horizon, and now we are supposed to go beyond. Okay, so there's beyond the horizon. Becomes difficult, and I prepared some 3 topics. I would like the younger members of the audience to choose one of them, and if you let me do 5 more minutes.
We
Okay,
still have 5 minutes.
so what are the the 3 topics are, first one will be what are the finite schemes in algebraic geometry, and how to define the cactus varieties. So this will be this last slide, and I would very briefly tell you what are the finite schemes and how to use them to define cactus varieties. Second will be seemingly independent of the rest of the talk, which it's about commutative algebra. This is a problem that I've encountered in my research, and I cannot solve yet, and maybe you will be able to help. And the phrasing is relatively elementary, but it's in purely commutative algebraic language. And then I can also talk more about the matrix multiplication exponent that appeared a little bit before, and then the role of algebraic geometry in its study. So I'm taking votes now, or maybe not votes. Number 2 and 2, 1, 1.
Which number?
I mean, I leave it to chairman to organize the vote at the count.
It looks like the majority.
Majority is voting for 2, or is it?
Definitely fewer, yes. How about a 3? No, 2 is done.
Which one, 2 or 3?
Well, definitely 2 is the majority, obviously.
2. Okay. Now how do I go use this? Okay, it doesn't work. So I have to scroll, unfortunately, because the thing is not working. So this is crash course of, okay. So this is about saturation of ideals. And then, this commutative algebra operation called colon ideal is something that let us represent the difference of 2 geometric objects. This could be varieties or union of different varieties, and to some extent, well, I will show you an example in a minute, but the formal definition, this colon ideal, is you take a commutative ring, you take 2 ideals inside this commutative ring, and then the colon ideal is the set of all those elements in S, such that if you take S and multiply it by this second ideal, J, then the whole thing is contained in I. So it's a little bit, I mean, why is it called colon ideal? Maybe this example shows you if you take a polynomial ring and you take nice prime ideals J and K, then you can form a product ideal J times K, which is just generated by J times K through all elements of J and K. And then we always have that K is a subset of this colon ideal. And in nice situations, most situations we will have equality. I mean, some of you will come up, if I say that all of them, then some of you will come up with counterexample. That's fine, but very often this is the case. So that's the reason why it's called colon ideal. So it's like division of ideals, okay? And as with division often happens, it's not always perfect. But that's the example. And then the example that shows how does it correspond to difference. If you take S to be polynomial ring in 2 variables, and then I would be the ideal of all polynomials that vanish at this 3 points. These 3 points. Okay. The one marked green on the slide. So this is my I. I take as J the equation of the line passing through one of them. What I get as a result is the ideal of all polynomials then vanish at remaining 2 points. So this is what happens. So I'm taking I, the set corresponding to I. I'm getting rid of everything that hits blue line. Maybe if this was positive dimensional, then I also need to take the closure of what remains. And then this is what I get as a result. So this is like commutative algebra operation for geometric difference between two objects. And then you can see that this calculation is correct by just simplifying a little bit the formula. So you can get rid of this beta here and this alpha here by using the other element. This beta and this alpha, and then you can get rid of them using this one.
Sorry, Arek, am I right to think that if J is contained in I, then A divided A colon A, J is just the whole ring, right?
Yes, there is something like that. I'm not sure I followed the correct inclusions in your.
Okay.
But this is the case. Yes. So if you get rid of them, then the calculations becomes easy to check that both of these elements are in the column ideal, but then you also need to check that this is everything. And another example, maybe monomial ideal in 3 variables is like this, that if you take the column ideal with this J, which has all variables there contained in J, so alpha, beta, gamma. So it's like it's a huge ideal, and then well, in the first step you don't do much. You just add, you reduce this number 3 to number 2, and then in the follow-up, if you do it second time, you already reduce it to much smaller ideal. And then it stabilizes. So it's a general feature. If you keep doing column ideal with respect to the same ideal, then eventually we'll get something that's stable. So it will be always the same. So now the relative linear algebra problem that I want to mention. So now first the theorem, like from elementary linear algebra, more or less. So if we have a field, oh, sorry, K should be, well, it could be over any case, but I've switched from C to K at some point. So you either change K to C or C to K, whatever is your preference. If you have a polynomial ring with coefficients in a field, we think of it as a graded ring, so we give a degree to each alpha I. We say that this is just 1. So the way we measure degrees is just a standard one. We just add the exponents of each monomial.
So you mean homogeneous in terms of a degree, right?
If you have a homogeneous polynomial, then you can say what is degree. But this is a graded ring, meaning that it's a direct sum of its homogeneous pieces. Okay.
Yes, but every variable has degree 1, so I think that the meaning of homogeneous is straightforward, yes?
Yes, it is. This is a preparation slide. I want to make sure that we understand this, and then there's a space where I will fill in some other stuff, and then it's going to be slightly less intuitive. So the known statement is a standard statement is that if you have ideal, which is very simple, it's generated by homogeneous elements of degree at most 1. So like, what are the homogeneous elements of at most 1? Either a constant or a linear form. Then, if I take the column ideal of I with respect to this maximal idea containing all the variables, then it's either I or the whole ring. So this is, if you contemplate it a little bit, you will find out that this is fairly straightforward. And then I will rephrase it a little bit. Oh, this infinity should be gone from here, so just ignore the infinity sign. And if I take if I rephrase it a little bit, it just says that the colon idea, the same colon idea, is generated in degrees at most 1. So this is a theorem that's not difficult to prove. It's in terms of algebraic geometry, it tells you that the ideal of a linear subspace in projective space is generated by linear equations, roughly. Right? I mean, it's nothing very fancy. There's, but what I want to change is that the base ring is not a field anymore, but it's an algebra, K algebra. Maybe you want to assume that K is algebraically closed here, maybe not. And now I'm taking the polynomial rings whose coefficients are in A. And now I also want to think about it as a graded ring, a polynomial graded ring, and then the constants A are all of degree 0, and then degree of each variable is equal to 1, and then the open problem that I don't know how to solve is this conjecture that the same happens as before. So I take an ideal inside this polynomial ring, but with coefficients in K algebra, or in any ring, commutative ring, even if you are brave. Then you take homogeneous ideal generated by elements of degree 1, maybe degree 0 as well, but the degree 0 guys are not very relevant, so degree at most 1. And then you take the colon ideal with respect to all positivity, all elements of positive degree, and in the end you get something that generated in degrees at most 1. So that's the conjecture. At this moment, I'm not entirely sure this is true. I'm not entirely convinced it is true, but it would be interesting to know for me, and it also was a step in some of my plans for research. I'm not saying that if you solve this conjecture that this will certainly push forward the research, but this is a step, right? Both a counterexample and a proof would be interesting to me.
But not both.
Well, better not both. Although I imagine that, for example, you can have it's possible that this is true under some additional assumptions about A, but it's not true if A is very nasty.
Yeah, exactly. That's what I was thinking about. So what kind of assumptions would you imagine?
Right. So I would like to be the applications that I have in mind. So I want K algebraically closed, and A would be a finite algebra over K, which means that this is as a vector space over K, A is the finite dimension. But if you give me a counterexample or proof for a different class of rings, I will also be interested to see. Okay, thank you this time.
Thank you very much.
Sorry for going over time.
No worries. So we had a peek beyond the horizon, so your talk was not a black hole.
Yes.
Okay, any questions, please? Adam?
Thank you for the beautiful talk. So you mentioned, of course, secant varieties. And we know that, for example, Segre variety and Veronese variety arise naturally while talking about decompositions. And we also know that finding equation of the secant variety is an open problem. So I was wondering, what can we say about the equation of secant varieties? Like how close are we to finding this equation? I know that there's a case in which we are, in the case of the rational normal curve, we were able to find the equation, but like, what are the main ideas we have, or where is the research going? And then I also wanted to ask if we were able to find equation of the cactus variety, since it's this more general variety that we introduced. And last one, if I can also ask an intuition on what a cactus variety is, because I've never heard of it. I've heard of it, but I've no idea what a cactus variety is. So even like an informal, an intuition on what a cactus variety is.
Okay, there were many questions. I'm not sure if I will be
Remember.
able to cover them all. Okay, so we are very, very, very far away from knowing the equations of secant varieties. And the main reason is because whatever we try to find, I didn't say that explicitly, but if we address the problem of secant varieties, well, we have some idea, and then we are very happy. It makes some progress, and then we check carefully. It turns out that the criteria that we found out actually are criteria more for cactus varieties, so they always show up in a nasty way. And then on the other hand, cactus varieties are easier to describe in the terms of equations. So we have some results about the equations of cactus varieties, and this will be a topic for 3 other talks. And then to cover all of the cases where we can do it. And then was a question about what are cactus varieties. Well, sorry, you've lost your vote. I knew there is no chance of. I mean, it's the democracy, right? It's not everybody wins.
Thank you.
Okay, anybody else?
Yes, so I was wondering if these
Could
second
you tilt the microphone?
Oh, okay.
Yeah.
Right now? Okay, so I was wondering if second varieties have any like functorial properties. Let's say they have a functor that they represent, something like this. This is the first question. The second one is, are second varieties for an affine scheme affine, or they are not? And the third one is, I know that it somewhat relates to Gorenstein algebras. Can you please describe how exactly, like cacti varieties?
Okay, so there are again many questions.
Yes, it's a multi-question.
And maybe the answers will be similar, at least the last one. Okay, so the first one was, is there are functorial properties of secant varieties? So yeah, I understand this is the fashion now to describe everything in terms of functors. I'm a more like down-to-earth mathematician, and I prefer to real-life objects. As you have seen in my first slides, I want them to be somehow related. Well, somehow, okay, not related to real life, but somehow explained in terms of simple and real life, so that if my grandma asks me at the dinner during the Christmas Eve what I'm doing, I can kind of explain. And then, so secant variety depends on 2 things. One is X, the geometric object X, and the other thing is the projective or affine space that it's embedded in. So there's a X, affine space, and embedding, right? So now you would have to work with that. So secant varieties behave well if you use linear maps. So if you have a map from V to W, and then you take the image of X and you take the image of the secant varieties, then there is, at least for secant varieties, there is I think equality, if I remember correctly. And then so you can make a functor from the category of linear maps, from category of vector spaces, and then with linear maps into something. So you need also to include the embedding of X in your projective space, and then with this you can do some tricks, and there are okay. So I'm not saying this is not being used in the background. There are some stuff there, but this is not. It's not so it's not very often that your X that you work with, it happens sometimes, but not very often. Your X you work with is an image of something from the larger projective space under a linear projection. Okay, so this would be like separate category for. I mean, there will be a bunch of disjoint components of this category, which are hard to relate in the functorial way, because you don't have linear maps mapping one into the other. And
Okay.
what was the other questions?
The other ones were, is second variety often affine or is it not? And the third one was, how does it relate to
Okay,
Gorenstein
so the
algebras?
third one I remember. The second question. So the way I presented it on the slides was, yeah, everything was affine. I mean, I start with an affine variety X, and then I take a closure of the of some set, and then I didn't say what topology I mean, but for most cases it wouldn't really matter. For the interesting cases, it wouldn't really matter. And yes, the closure is, at least over an algebraically closed field, the closure is again an affine variety. But I'm a projective geometer, and I do everything in the projective space, and then everything is projective instead. And that's a little bit easier because projective space is compact, but it's more perhaps demanding to explain what's linear span in projective space and so on. And then the third question was about cactus varieties again. Yes, Gorenstein schemes appear there, and well, I don't remember what you voted for, but the majority voted for two.
Okay, thank you very much.
Okay, anybody else? Adam, go ahead.
Okay, so regarding this problem of matrix multiplication, is it known whether this exponent is optimal, and if not, what is expected? Log base 2 of 7.
Right. So I guess that's the same answer, right? I mean, this would be covered in the topic number 3, but the vote was for 2. Okay, I can explain you guys afterwards, but not here, not in the. If you come afterwards, I can explain this to you.
Now let's see if there's anybody on Zoom who wants to ask a question. Hello, Zoom people. No raised hands. Okay, so let me finish by asking you some questions. My first question is, what is it a picture of? It's not Ben-Levo, is it?
It's not Ben-Levo. So every story, every of those last stories had a different picture at the end. So the conjecture is related to a notion of familiar that we are going to introduce in the upcoming paper. And familiar is, well, in algebraic, in the language of geometry, it's supposed to be an abbreviation for family of schemes of degree at most R, which are not something something. So there's abbreviation of familiar, but in the English language, familiar is an animal that's served to witches and cunning folk in the medieval times, and also later, such as cats, dogs, maybe toads or something like that. And they were supposed to be demons in things. So that's why the cat is here. And this is the castle where the cat lives. It's in Xàtiva in Spain.
In Spain.
And
okay, so this explains both the cat and the chateau. Now, my more mathematical question is, could you please somehow give me very briefly and succinctly an idea, because this is where I got lost. What is the relationship between these secant varieties and decomposition problem?
Right. So the composition problem was this is not yet here. So the composition problem was to take an element of the vector space and then try to write it as a linear combination of points from X. And then the secant variety is the set of all the linear combinations of points and the closure. So it's almost the same up to this closure. And it's easier to deal with geometrically with secant varieties than to deal with this kind of part before closure because it have not very nasty structure. But these are the limits, right? This is the limits that are swept under the rug. This is one of the few things that I was cheating a little bit.
Okay, thanks. And let me end with a comment. You see, Jarek represents algebraic geometry. I represent non-commutative geometry. So maybe it's good to give you an idea how we differ. So both theories kind of stem from Jascher's. You had Grothendieck and Alencon, both in Jascher's. And when you look at a very simple object, say, the algebra of continuous functions on some nice compact Hausdorff space, or maybe some algebraic subset of complex plane, whatever, and just look at algebra of functions. Well, it has many nice properties. One of them is commutativity, but another of them is that, for instance, there are no self-adjoint nilpotents and so on and so forth. And in non-commutative geometry, we keep all the nice properties except for commutativity. We forget commutativity, but we want to have no self-adjoint idempotents. We want faithful representations on the Hilbert space, all these sister algebras which Sultan was talking about. And in algebraic geometry, it's kind of the opposite. They keep commutativity and forget everything else. And this is how they get into all these schemes and affine schemes, ringed spaces, whatnot. So if you would like to explain to somebody, to your grandma at Christmas Eve, yeah,
Yes.
What's the difference between algebraic geometry and commutative geometry, that's the way to go.
Yes, exactly.
Okay?
Yes.
Okay.
That was a part. That was on story number 1. That was a
Yes.
part of the story number 1.
Perfect. Okay, so let's thank Jarek again for his absolutely wonderful talk.
Thank you.
And we adjourn.